The first soft note, what Webb was listening for. In the quiet cradle of deep space, far beyond the warm embrace of our sun, the James Webb Space Telescope drifted like a gentle listener leaning closer to a cosmic lullaby. It wasn't searching for loud explosions or dramatic flashes, but for the faintest whispers stitched into the darkness, the kind that most telescopes had overlooked because they seemed too subtle, too shy, too fragile to be real. Webb's instruments, tuned with extraordinary sensitivity, were poised to capture these soft vibrations, tiny stretches of space, slight wavers in ancient light, and murmurs carried across billions of years. It was as if the telescope waited with closed eyes, breathing slowly, preparing to hear a note from the universe that had remained unsung to human ears until now. And as the darkness wrapped itself gently around the golden mirrors, the telescope listened further, letting those delicate frequencies brush over its sensors like cool night wind passing through curtains. Each particle of light arriving at Webb was ancient, older than Earth itself, older even than the first stars that lit the cosmos, carrying signatures that spoke in subtle tones. In these tones, scientists suspected something was hiding, a presence heavy enough to bend galaxies, powerful enough to distort time, yet invisible to all who looked. Webb wasn't searching for chaos, it was searching for the softest disturbance a black hole might leave behind, not in its violent hunger, but in its calm, steady pull on the universe's fabric, a sign of something impossibly massive existing impossibly early. For millions of seconds, the telescope drifted in silence as the universe continued its slow, graceful expansion. The early cosmos, which once roared with fire, now hummed with memories, and Webb sifted through them like someone reading old letters written in fading ink. What it hoped to find was a gentle trembling, a soft note, woven into the oldest light that traveled to its mirrors. A note that shouldn't have existed because theory said it couldn't, not so soon after the dawn of creation. Yet the universe has a way of surprising those who listen carefully, and Webb was listening as though the entire cosmos had leaned close to whisper a secret only it could hear. And when the data began to trickle in, slow and smooth like ripples spreading across a still lake, researchers felt something familiar yet entirely new emerging. It wasn't a bright flare or a violent outburst, but a dim dip in brightness around a small, distant galaxy, so distant that its light left when the universe was still learning how to build its first structures. This faint dip wasn't accidental. Light had been stretched, slowed, and reshaped by something extremely dense. The telescope's delicate ears had heard something pulling on that ancient glow, something deep and quiet, the way a heavy stone beneath the sand makes the surface sag without making a sound. This was the soft note Webb had been listening for. So the scientists leaned closer to the data, letting the calm of the discovery sink into them like the slow descent into dreams. They knew that only the most massive objects in the universe could bend light so gracefully, leaving behind curves and distortions so smooth they resembled the strokes of an artist's hand. But this wasn't supposed to be possible at such an early time. The cosmos was too young. Stars were still learning to shine steadily. Galaxies were just beginning to assemble like newborn puzzle pieces. And yet something massive, hugely massive, was already there, shaping the light around it with the gentlest gravity-woven fingerprint. Then came the slow realization: the soft note belonged to a black hole. But not an ordinary one. This black hole was enormous, millions of times the mass of the Sun, and it existed when the universe was still in its infancy, just a few 100 million years old. According to every model and simulation, such a thing should have taken billions of years to grow. But here it was, humming softly across time, discovered not through its roar but through its whisper. Webb had heard it because it was designed to hear the quiet things, the things hidden beneath the cosmic noise, the things that spoke gently yet carried profound meaning. As the discovery settled into the minds of researchers, a strange kind of calm accompanied the shock. It was as if the universe had quietly placed a hand on their shoulder, guiding them toward a truth they were now ready to uncover. The early universe hadn't been peaceful or simple, it had been restless, creative, and full of possibilities far beyond what calculations allowed. This black hole, this enormous, softly singing anomaly, was a reminder that cosmic growth could happen in ways still unknown, ways that were slow, smooth, and impossibly efficient, like a river carving a canyon with patience rather than force. And the story of this discovery began to feel more like a dream than a scientific report, with Webb floating silently in its orbit, listening to the hums of the ancient universe like a traveler listening to the wind across an endless desert. The light bending around that primordial black hole carried with it the scent of cosmic dawn, the echo of the first stars, the warmth of newborn galaxies gathering themselves. Webb had captured something more than data. It had captured a feeling, a soft and nearly invisible thread connecting humanity to the earliest moments of existence. Researchers studied that soft note again and again, layering observations, comparing shapes, measuring curves in the light. Each new pass revealed more depth, more certainty that the distortion wasn't a mistake or an illusion. The black hole was undeniably real. It had shaped its surroundings with a delicacy that felt almost gentle, though its mass could swallow millions of suns without hesitation. And this contrast, its quiet signature versus its unimaginable strength, was part of what made the discovery so soothing, almost like listening to a deep voice speaking slowly in the dark. The more they analyzed, the more the data wrapped itself around them like a warm, cosmic blanket. The universe was not merely expanding, it was telling a story. Not in shouts or echoes, but through the smallest inflections of ancient light. It told of young galaxies growing faster than expected, stars being born in bursts of brilliance, and black holes forming with mysterious efficiency. The early cosmos had been filled with soft notes like these, but only now did we have the ears to hear them. Webb's sensitivity became a kind of poetic gift. It could catch the faint glow of dust warmed by early stars, the gentle stretching of space shaped by gravity, the dim colors drifting through galaxies that existed before Earth was even a dream. And in this gentle glow, the soft note of the ancient black hole persisted, steady and calm, like a heartbeat echoing from the past. Every time the data was re-examined, the note grew clearer, smoother, more undeniably real. Scientists began to wonder how such a giant could have emerged so early. Theories shifted softly, like blankets being rearranged in the middle of the night. Some suggested the seed black hole must have been enormous to begin with, born from the direct collapse of a massive cloud rather than the death of a star. Others thought the early universe must have been more fertile than expected, feeding baby black holes with rich streams of gas that let them grow quickly. Each explanation flowed gently into the next, as no single idea seemed to fully capture the quiet enormity of what Webb had found. But even as the mystery deepened, the cosmic calm remained. There was a beauty in not fully understanding, a soothing wonder in realizing that the universe still holds secrets vast and patient enough to unfold only when the right listener arrives. Webb, with its golden petals open like a flower in the dark, had become that listener. It was hearing the universe not as noise, but as music, each soft note a clue to a deeper truth. The more the measurements came in, the clearer it became that this black hole was not alone. There were hints of others, perhaps many others, hidden in the early cosmic dawn, each leaving behind faint distortions in light, each humming its own soft gravitational tone. The early universe might have been filled with these sleeping giants, growing quietly beneath the first stars, shaping the cosmos before galaxies even knew their own forms. And this realization brought with it a deep, almost hypnotic sense of scale. Human lifetimes felt tiny, fleeting sparks compared to the vast, slow rhythms of cosmic growth. Yet through Webb's gaze, humanity was able to tap into these ancient pulses, feeling the universe breathe through light that had traveled across epochs. This connection, delicate yet powerful, made the discovery feel intimate in a way scientific measurements rarely do. As the story grew, Webb continued listening, turning its quiet attention to other faint signals, letting the universe speak naturally, without forcing interpretations or expecting familiar answers. The telescope was teaching scientists to move slower, to listen more gently, to trust the small details that usually slip by unnoticed. In this patience, more truths were likely waiting, truths that might once again reshape our understanding of how the cosmos grew from darkness to brilliance. The soft note of the ancient black hole became a symbol of this patience. A reminder that gravity itself hums quietly, pulling, stretching, sculpting space with motions so slow they can be mistaken for stillness. But within that stillness lies unimaginable power, the kind that builds galaxies and guides the motion of stars, the kind that whispers across billions of years and still reaches us intact. Every night, as Webb drifted in its silent orbit, that soft note continued traveling toward its mirrors. It was a lullaby from the early universe, a tune shaped by a black hole born too early, grown too quickly, existing too boldly for old models to explain. Yet here it was, singing through light, through time, through the deep, velvety silence. And finally, as scientists pieced together the full picture, they realized the soft note wasn't just a discovery, it was an invitation. An invitation to look deeper, listen longer, and drift gently into the mysteries woven into the first chapters of cosmic history. It asked them to imagine a universe more creative, more daring, and more graceful than they had ever allowed themselves to believe. And in that slow, soothing realization, the story of Webb's most delicate discovery settled like a quiet dream, guiding listeners into a deep, peaceful rest, where the universe becomes not a puzzle to solve but a gentle melody to follow through the long night. In the vastness of Webb's deep-field images, where galaxies stretched like painted brushstrokes across the canvas of early space, one tiny red dot glowed with a quiet persistence, almost shy in its presence. It wasn't bright, nor was it dramatic, it flickered faintly, as though wrapped in a soft cosmic haze. Yet something about it seemed to pulse gently, like a small ember holding on to warmth long after the flames had died. Scientists zoomed in again and again, each time realizing that the dot had a strange steadiness to it, a delicate hum hidden within its light. This wasn't the kind of galaxy that screamed its existence into the void. It whispered, patiently waiting for someone to notice its rhythm. The tiny red dot existed so far away that its light had traveled for over 13 billion years, crossing the entire age of the universe to reach Webb's golden mirrors. Because it was so distant, it looked stretched and reddened by the expansion of the cosmos, like an old photograph touched by the soft tint of time. But beneath this redness, beneath the faint glow, was something structurally unusual, something that made astronomers pause. The dot wasn't chaotic or scattered, it was compact, concentrated, almost too mature for such an early era. It held a density that suggested something massive rested inside it, shaping its light with a firmness that felt strangely calm. As researchers measured the faint fluctuations in brightness, they noticed the light dipped at intervals too smooth to be accidental. Light from behind the galaxy seemed slightly curved, slightly delayed, as if passing through a gentle gravitational pocket. It wasn't strong enough to warp the image dramatically, but it was consistent, steady like the soft thrum of a string plucked far away. This hum in the data hinted at an intense gravitational presence buried at the center of the tiny red dot. It wasn't the turbulence of starbursts or the wild lights of collisions, but something quieter, heavier, and far more stable. This stability intrigued researchers because galaxies from this era, just a few 100 million years after the Big Bang, were usually messy and unorganized, like children still learning to walk. But this one behaved differently. It had the smoothness of a system that had already settled, as though something deep inside it had anchored the surrounding stars, preventing the chaos that typically characterized early galaxies. But what could do that? What could hold such young, fragile structures together so firmly in such a short cosmic time? Webb's instruments continued to gather data, and every new layer added thickness to the mystery. Spectral lines revealed rapid motion, stars swirling around at speeds that should have torn such a small galaxy apart. Yet nothing was breaking. Nothing was flying away. It was as if an invisible heart beat in its center, a heart heavy enough to bind everything in a tight gravitational embrace. Scientists began to whisper among themselves that perhaps the tiny red dot wasn't just humming metaphorically, perhaps something within it really was emitting a gravitational note, a soft, steady resonance left by a growing black hole. But how could a black hole of that scale exist so early? The universe at that time should have barely begun forming stars, yet here was an object already mature enough to influence an entire protogalaxy. Some theories suggested that in the early universe, gas collapsed more efficiently, forming massive black holes directly rather than starting small. Others proposed that this system might have merged with several smaller galaxies, pulling all their mass together. But the hum, the steady gravitational curve, found in the data suggested something more serene, more singular, more quietly dominant. As scientists studied the tiny red dot, they began noticing that the hum wasn't uniform, it had subtle variations, like a soft melody drifting from another room. These variations lined up with the signatures of stars orbiting something extremely dense. Each orbit left a faint mark in the spectra, a tiny wobble too coordinated to dismiss. These wobbles suggested a central mass millions of times heavier than the Sun, tucked neatly inside a galaxy smaller than some of the ancient star clusters in the Milky Way. The presence felt impossible, almost magical, yet undeniably real. The hum grew more meaningful the deeper they looked. Instead of being a chaotic blend of signals, it began to reveal itself as a calm gravitational drumbeat, steady and patient. This steadiness implied the black hole had been feeding at a controlled pace, not wildly devouring gas as young black holes often do. Somehow, it had grown large enough to dominate its galaxy, yet quiet enough to avoid tearing its environment apart. It was the cosmic equivalent of a giant creature sleeping peacefully, its slow breaths shaping everything around it. The faint redness of the galaxy shifted subtly in different wavelengths, revealing that dust was already forming around it, a surprising fact for such an early time. Dust usually took generations of stars to produce, yet this tiny dot seemed full of it. This dust glowed softly, warmed by radiation from the central black hole, adding yet another note to the hum, an infrared whisper that Webb caught with tender precision. The dust glow suggested steady heating, as though the black hole wasn't raging, but simply radiating a quiet warmth into the surrounding gas. As data poured in, astronomers began referring to the tiny red dot with a quiet fondness. It wasn't a dramatic quasar or a blazing stellar nursery. It was subtle, modest, but profound. It contained answers wrapped in softness, the way deep truths often come disguised as gentle moments. And within this softness, the hum revealed layers, mass, structure, motion, temperature, all pointing toward a gravitational titan hiding in a galaxy no larger than a cosmic seed. The more they observed it, the more the galaxy's calmness stood out. Most early galaxies flickered with unstable star formation, changing brightness like candles in the wind. But this one held steady, its light barely fluctuating, suggesting that its central black hole had acted like an anchor, bringing premature stability to a place that should have been turbulent. The hum was not just gravitational, it was emotional, almost like the universe exhaling slowly. Scientists ran models, simulations, and reconstructions, trying to recreate how such a system could have formed. Most scenarios failed. Stars formed too slowly, black holes grew too gently, and structures remained too soft to match the density of the tiny red dot. Only when they allowed exotic conditions, massive direct collapse black holes, streaming cold gas flows, or collapsed primordial clouds, did the models come close. Yet even then, the hum in the data felt smoother than any simulation predicted. This smoothness raised a quiet suspicion. Perhaps the early universe had far more efficient black hole nurseries than previously believed. Perhaps these ancient giants weren't rare outliers, but common melodies in the cosmic dawn, simply unheard until Webb had the sensitivity to listen. The tiny red dot might be only the first whisper of a much larger cosmic choir waiting to be discovered. And with this idea, the hum transformed from a question mark into a doorway. It suggested that black holes might have shaped the first galaxies more intimately than ever imagined, not through violent outbursts, but through subtle gravitational sculpting. They might have been the silent architects of cosmic history, assembling the earliest structures with a gentle pull rather than destructive force. Night after night, the telescope kept returning to the tiny red dot, collecting more photons, refining its details. The hum persisted, unwavering. It was steady, soft, and patient, like a heartbeat echoing from the first moments after creation. Each observation deepened the mystery, but also deepened the calm surrounding it. The dot was like a lantern glowing faintly through cosmic fog, guiding scientists somewhere unfamiliar but compelling. Eventually, the hum became unmistakable evidence. Something impossibly heavy existed in the tiny red dot. Whether it was a massive seed black hole or an early supermassive one already grown beyond expectations, the conclusion remained the same: the universe had been more ambitious in its youth than theory had dared to suggest. Researchers sat with that realization quietly, letting it settle over them like the warmth of a blanket pulled closer in the night. The tiny red dot had spoken, not loudly, but clearly. And in its quiet hum, it invited humanity to rethink the earliest chapters of cosmic evolution, encouraging a gentler, more imaginative view of how the universe first dreamed itself into being. Even now, its light continues to travel, carrying its soft gravitational song through the endless dark, humming across cosmic distances until someone, somewhere, listens again. The surprise: monster black holes in little galaxies. When scientists finally allowed themselves to sit still with the data, letting the patterns wash over them like the slow tide of a quiet beach, they came to the realization that felt both thrilling and unsettling. There were not just small hints or faint distortions pointing to black holes in the early universe, there were signs of monsters, of giants, of gravitational titans crouched inside galaxies that were themselves no bigger than cosmic seedlings. These galaxies were far too small, too young, too fragile to host such enormous structures, yet Webb's observations left little room for doubt. It was as though the entire cosmic story had skipped ahead several chapters, revealing mature beasts where only infants were expected to exist. And the strangeness of it became even more pronounced the more the researchers examined the shapes and flows of light in these galaxies. Instead of chaotic, scattered motion, the stars within these tiny galaxies whirled around as though firmly tethered to an invisible anchor. That anchor had to be massive, so massive that it rivaled black holes found in galaxies hundreds of times larger. How could such grotesquely oversized objects have taken shape inside such delicate, early structures? The mismatch felt almost comical, like discovering a sleeping giant curled inside a child's cradle. Yet the data showed no trembling, no instability. The galaxies seemed somehow comfortable with their oversized residents. As they studied this cosmic mismatch, astronomers realized it presented a deeper question. Were these monster black holes truly anomalies, or had the early universe been brimming with such mismatches all along? If Webb's sensitivity had revealed even a few of these objects so quickly, it might mean the universe was seeded with massive black holes much earlier and much more efficiently than previously imagined. Maybe the early cosmos wasn't a slow builder but an ambitious architect, constructing colossal gravitational wells before galaxies even had time to settle into their own forms. Yet the black holes themselves seemed strangely calm. They didn't blaze with the fierce, ravenous hunger of typical quasars. Instead, they glowed with a subtle, steady warmth, as though feeding gently rather than tearing apart everything around them. This quietness ran counter to the violence scientists expected from early black holes, which should have devoured gas in wild, luminous bursts. Instead, these monsters behaved like serene, ancient beings, exerting influence not through rage, but through patient gravity, guiding their galaxies with a gentle but unbreakable hand. This gentleness only deepened the mystery. If these black holes had grown so large so early, they should have left behind scars, violent outflows, disrupted stars, shredded dust clouds. But the galaxy's web detected around them appeared strangely orderly, like small villages built around a massive, silent temple. The stars showed motion, yes, but it was coherent, almost disciplined. The gas flowed in patterns that suggested structure, not destruction. The monster black holes did not seem to have bullied their galaxies into shape. Rather, they seemed to have nurtured them, providing a gravitational core around which everything else quietly settled. The surprise grew even deeper when scientists realized that these black holes didn't fit traditional growth models at all. To reach such mass so early, they either had to start impossibly large or grow impossibly fast. But neither scenario matched the calm signatures Webb observed. Rapid growth would have created turbulence and light, while colossal birth would imply processes far beyond what stars alone could provide. Instead, it looked as though the universe had taken a shortcut, forming large seeds from direct collapse, massive primordial clouds collapsing straight into black holes without ever making stars first. Such a process had been theorized but never confirmed. Webb's discovery now offered the strongest hint yet that the early universe may have had entire regions where star formation was bypassed entirely in favor of birthing giants in silence. These black holes, born in darkness, would have become the quiet gravitational kings of their tiny realms, shaping galaxies from the inside out with soft precision. The idea felt both eerie and elegant, a cosmic ballet unfolding without light or fireworks, but with immense, invisible force. As the models shifted to account for this possibility, astronomers found themselves faced with a universe far more active at its dawn than they had ever pictured. Instead of taking millions of years to assemble small star clusters and then slowly merging into galaxies, the universe seemed to have skipped ahead, forming structures with astonishing speed. The monster black holes were clues, gentle but undeniable, that gravity had played a much more aggressive, early role than previously believed. The galaxies themselves seemed to cradle these giants with surprising tenderness. Their shapes weren't torn or stretched, but compact, almost protective, as if they grew around their black holes like shells forming around a pearl. The stars inside them orbited with remarkable balance, creating gravitational harmonies that Webb's instruments captured with delicate accuracy. These small galaxies, despite their youth, moved as if guided by something ancient, a strange feeling considering they existed so close to the universe's beginning. And as scientists compared the galaxies, they found similarities that made the phenomenon even more intriguing. The galaxies were small, dense, red, and tightly bound. Each hosted a central mass that was far too large for its size. Each emitted steady rather than chaotic light. And each behaved as though it had been shaped by a calm, central presence rather than the violent forces expected at cosmic dawn. These black hole-dominated galaxies weren't accidents, they were a pattern. The realization washed over the scientific community slowly, like morning light spreading across a quiet valley. Monster black holes in tiny galaxies might not be rare, they might be the rule. Their existence could rewrite the early chapters of cosmic history, suggesting that the first galaxies were not scattered, delicate structures but compact, tightly anchored systems built around gravitational giants. The giants themselves may have acted as seeds, drawing matter around them like soft whirlpools, accelerating galaxy formation rather than hindering it. The implications of this discovery extended far beyond the early universe. If black holes formed early and massively, they could have influenced large-scale cosmic structures, clustering galaxies, shaping filaments, and determining the distribution of matter. The universe's iconic web-like structure might have been sculpted not only by dark matter but also by the subtle, early guidance of monster black holes nestled inside baby galaxies. As Webb continued to observe these systems, it found hints that some of them were already merging. Tiny galaxies with giant hearts drifting toward one another like floating lanterns drawn together by unseen currents. Their black holes, too, may have danced into proximity, potentially forming colossal binary systems long before the universe even reached its toddler years. These early mergers could have sent gravitational waves rippling across the cosmos, waves still traveling through space, soft and stretched by billions of years. Scientists wondered if future instruments might one day detect these ancient ripples, connecting them to the exact galaxies Webb had uncovered. The thought was soothing, a cosmic thread weaving data across unimaginable spans of time. It added yet another layer of calm beauty to the discovery, reminding researchers how interconnected the universe could be, even across eons. But at the heart of the surprise remained the simple contrast that made the discovery so mesmerizing: enormous black holes resting inside galaxies much too small to contain them. Yet the galaxies didn't shatter. They didn't collapse. They flourished quietly around their central giants, as though the black holes provided a gentle gravitational heartbeat that kept everything steady. The balance was delicate but strangely peaceful, like a mountain resting on a cloud yet somehow remaining upright. The more the data came in, the more this cosmic balance seemed intentional, an unspoken rule of early galaxy formation rather than an exception. The galaxies turned out to be dense, star-forming, and stable, not in spite of their black holes, but because of them. The central giants may have warmed surrounding gas, preventing chaotic collapse, allowing stars to form in gentle waves instead of explosive bursts. It was a nurturing kind of gravity, the kind that held things together quietly. As the story took shape, scientists found themselves speaking about the early universe in softer tones. The discovery felt like uncovering a quiet truth rather than a violent revelation. Monster black holes didn't always roar, they sometimes whispered. They sometimes guided. They sometimes allowed galaxies to settle around them like small creatures gathering near a warm, steady fire. Even the terminology shifted subtly. They were no longer just early black holes. They became cosmic anchors, primordial hearts, silent giants. The language reflected the calmness of their signatures, the peace they seemed to bring to their host galaxies. It was a poetic turn, but an accurate one. The data showed serenity where chaos was expected. And so, as the scientific world re-evaluated the foundations of cosmic evolution, Webb continued to listen. More tiny galaxies revealed more oversized black holes, each adding another verse to the quiet song of the early cosmos. The surprise became a story, then a pattern, then a new understanding. The universe, in its earliest hours, had not been timid. It had been confident, efficient, and quietly ambitious, building enormous gravitational engines inside the smallest of structures. And in discovering this, humanity was granted a new kind of cosmic lullaby, a deeper, gentler hum beneath the fabric of existence, guiding imagination into the soft mystery of how everything first began. How we know, the light that tells a tale. When scientists set their eyes on the faint, stretched glow from these distant galaxies, they were not simply looking at light, they were looking at history carved into photons. Each tiny flicker had traveled across almost the entire age of the universe, carrying memories of collisions, collapses, and quiet expansions. This ancient light arrived bruised and reddened by the long journey, its wavelength stretched like a whispered secret spoken across a windstorm. Yet within that soft, red glow were subtle codes, shifts, dips, and spectral lines that allowed astronomers to read the story of what lay inside those early galaxies, like clues hidden in the margins of an old, weathered manuscript. Because the galaxies were so distant, their light was extraordinarily faint, almost trembling at the threshold of detection. Webb's instruments, designed to catch even the most delicate hints in the infrared, gently collected these scattered photons and broke them into their components. When light is split like this, It becomes a rainbow etched with patterns, dark lines where atoms absorbed energy, bright lines where they released it. These patterns were not random scribbles but the universe's own handwriting, marking the presence of specific elements, movements, temperatures, and densities. Each line became a tiny window, a narrow but powerful view into the internal workings of something unimaginably far away. As the spectral signatures unfolded, scientists noticed behaviors in the light that betrayed the presence of enormous mass. When stars orbit around something dense, their motion imprints itself on the light they emit, stretching it when they move away, compressing it when they move toward the observer. This is known as redshift and blueshift, and in the data from the tiny galaxies, the shifts were far too extreme to be caused by simple stellar motions. They indicated stars whipping around at astonishing speeds, as though something massive was pulling them with unwavering gravity. It was a clear sign that at the center of these galaxies sat an object that possessed a grip far stronger than any cluster of stars could provide. Another clue came from the broadening of emission lines within the spectrum. When gas swirls rapidly around a heavy object, the atoms within the gas emit light that becomes smeared across a range of wavelengths. This smearing looks like a widening of certain spectral lines, and the extent of this broadening reveals how fast the gas is moving. In these early galaxies, the broadening was enormous, a silent scream embedded in the light, suggesting that gas was swirling around something with a gravitational pull millions of times stronger than a single star. The galaxy itself was too small to explain such speeds. Only a massive black hole could. The tale deepened when scientists noticed that the central regions of these galaxies emitted a subtle glow at specific wavelengths associated with heated dust. Dust grains warm up when exposed to intense radiation, such as the soft, steady energy released from material spiraling into a giant black hole. This warm dust re-radiates the energy in the infrared, creating a gentle, velvety glow that Webb captured with exquisite sensitivity. This glow wasn't chaotic or flickering, just warm, smooth, and persistent. It matched precisely what would be expected from a quietly feeding black hole, one that had settled into a stable rhythm rather than erupting with violent activity. As astronomers layered these clues together, the rapid stellar motions, the broadened gas lines, the warm dust signatures, they began to see a coherent picture forming. The light told a tale of central masses that were far too large for the galaxies that hosted them. These black holes weren't guesses or assumptions, their existence was inscribed in the spectra, each detail reinforcing the others until the entire system of clues clicked into place like a star map aligning with the night sky. The light wasn't just revealing the black holes, it was speaking about them with clarity and calm certainty. One of the most revealing indicators came from gravitational lensing. Although these small galaxies weren't powerful lenses themselves, their central masses subtly influenced the light passing behind them. The bending was faint but measurable, tiny arcs, slight stretching of background light. This minute gravitational curvature confirmed the presence of something extraordinarily dense. The galaxies alone did not possess enough mass to bend light so noticeably. Only an internal monster could create the soft gravitational ripple that Webb detected across multiple wavelengths. Another remarkable piece of evidence emerged in the form of time delays within the light itself. Light that passed closer to the central black hole arrived slightly later than light taking a more open path. These minute delays might seem impossible to detect, yet Webb's precision made them visible as a small but consistent effect across observations. It was like hearing two echoes of the same sound, one traveling through a narrow canyon and the other around its edge. This echo was gravitational, not acoustic, but it carried the same quiet certainty of a presence hidden deep within the tiny galaxy's core. Spectral analysis also revealed the ages of the stars surrounding the black holes. Surprisingly, many of these stars showed signs of early formation, with metallicities and temperatures suggesting that they had formed quickly and efficiently. This rapid assembly of stars aligned with the idea that a strong central gravitational force had helped concentrate gas early on, encouraging star formation in a compressed, accelerated way. The black holes weren't just present, they were shaping the story of the galaxy, helping it grow rather than tearing it apart. And this too was written in the starlight, encoded in the way stars aged, glowed, and moved. The galaxy's redshifts added another layer of insight. The farther an object is, the more stretched its light becomes due to the expansion of the universe. By measuring how much the spectra shifted, scientists determined that these galaxies existed only a few 100 million years after the Big Bang. That meant the black holes inside them had to have grown extremely fast, far faster than typical models allowed. The universe was still young, still finding its structure, yet these black holes were already giants. The light itself confirmed their age, making the mismatch between galaxy size and black hole mass even more breathtaking. Some of the most delicate evidence came from absorption features, certain dips in the spectra where cooler gas blocked specific wavelengths. The pattern of these dips revealed the distribution of gas around the galaxy. In these cases, the gas formed tight, spinning disks or compact clouds that hinted at orderly structure rather than chaotic flows. This was another quiet signature of a central mass exerting a gentle organizing influence. The gas wasn't swirling randomly, it was rotating coherently, as though obeying the silent instructions of an unseen force. Then there were the emission line ratios. Different physical environments, ionized gas near a black hole, star-forming regions, shock fronts, create different ratios of light at particular wavelengths. When scientists examined the ratios in these early galaxies, they matched those expected from low-level black hole activity. Not blazing quasar-level radiation, but a soft glow produced by moderately heated gas rotating in stable orbits. The light whispered, "Here lies a black hole not in frenzy, but in quiet growth." The galaxy colors also contributed to the story. Galaxies with active star formation tend to be blue because young, hot stars emit bright, short-wavelength light. But these galaxies appeared deep red not only because of cosmic redshift, but because their light was dominated by older, cooler stars and by dust warmed gently over time. This reddening reinforced the idea that the galaxies weren't exploding with star formation but were quietly simmering, their evolution guided by a patient central mass rather than frantic cosmic activity. Another subtle indicator came from the shape of the galaxies. Even in their tiny, distant forms, some displayed faint signs of rotation, elongated shapes, slight asymmetries, or hints of disk-like structures. This coherence suggested that these galaxies had established organized gravitational centers early on, likely influenced by the massive objects at their cores. Such organization was not expected in the chaotic early universe, yet the light insisted upon it, shaping the narrative with every new observation. The thermal signatures detected by Webb added yet another chapter. Dust and gas around these galaxies emitted heat with a smooth, predictable curve across the infrared spectrum. This thermal glow wasn't explosive or erratic, it formed a gentle slope, consistent with steady warming from a central source. The temperature distribution hinted at a black hole radiating energy at a moderate rate, enough to warm its surroundings, but not enough to create violent winds or outflows. It was a gentle furnace, not a roaring inferno. Astrophysicists also examined the galaxy's luminosity profiles, the way light intensity changed from the center outward. In normal young galaxies, these profiles tend to spike sharply or fluctuate due to irregular star formation. But here, the profiles were smooth, declining in a graceful curve that suggested a dominant central gravitational potential. The stars weren't clumped, they were distributed in a way that reflected the steady pull of a massive heart at the center. Light mapped gravity, and gravity pointed to the black hole. Even the faintest parts of the spectrum played a role in the evidence. Tiny bumps in the infrared continuum, almost like little breaths in the data, hinted at molecules and dust grains heated by gentle radiation, the kind emitted by material spiraling into a black hole. These faint features would have been invisible to any previous telescope, but Webb captured them in near silence, allowing scientists to read the softest parts of the cosmic story. When all the pieces of evidence came together, astronomers found themselves holding a tale that was both subtle and overwhelming. The light did not shout or flare, it whispered, layered, multifaceted, and remarkably coherent. It revealed not violence, but order. Not chaos, but calm. Not newborns struggling to form, but galaxies guided from their earliest moments by massive, steady gravitational anchors. In this way, the distant light became a storyteller, offering a narrative far richer than anyone had predicted. Through its shifts, glows, broadening, reddening, and warmth, it painted the portrait of monster black holes nestled inside tiny galaxies, shaping them with quiet authority. And in every spectrum, in every photon, the tale became clearer. The early universe wasn't just forming stars, it was forming giants, and the giants were guiding everything around them with soft gravitational hands. Thus the light, traveling across billions of years, arrived not merely as illumination, but as memory, an ancient, patient voice telling us exactly what lived at the heart of those first galaxies, inviting us to listen, to imagine, and to understand the quiet strength that shaped the cosmic dawn. Growing too fast, breaking the rules of time. In the dim, drifting quiet of the early universe, where galaxies were only beginning to gather their first delicate threads of starlight, something stirred with a pace that should have been impossible. It grew not like a young cosmic seed but like a creature already ancient, already hungry, already burning with a strength that didn't match the world it lived in. When the Webb telescope first traced its glow, astronomers expected the faint signature of a small black hole, the type that simply begins its journey, but instead they found something far more troubling: mass too large for its age, gravity too strong for its timeline, a behemoth. Pretending to be a baby in a universe barely waking from darkness. It was as if these black holes were skipping childhood entirely, rising straight into a maturity that should have taken billions of years to reach. Each measurement Webb took, each spectral whisper gently teased apart by its mirrors, reinforced the same baffling truth: these early giants were thousands of times heavier than the modest galaxies that cradled them. The rules of cosmic growth, slow accretion, steady feeding, long epochs of quiet accumulation, were being ignored with an efficiency bordering on impossible. Something about them felt rushed, urgent, like they were racing ahead of a universe not yet ready to host such monsters. The light that traveled more than 13 billion years to reach us carried within it the signatures of frantic activity, violent heating, swirling matter, and energy being torn apart in ways that required enormous gravitational power. But that power simply shouldn't have existed yet. The earliest stars were only beginning to ignite, the first galaxies were little more than feeble clusters of gas, and yet, hidden within them, these black holes were already feasting. The paradox grew louder the more Webb watched, turning what began as a scientific curiosity into a profound cosmic puzzle. Astronomers had long assumed black holes began as heavy but conventional remnants of the universe's first stars, massive, yes, but not exceptional. These primordial stars would collapse, forming seeds that would later expand through slow, cosmic patience. But the Webb results seemed to suggest those seeds had somehow skipped the intermediate steps, growing at rates so extreme that even the most generous models couldn't explain them. It was like discovering saplings turning into ancient redwoods in the span of a single season, ignoring the natural rhythms of growth and time. As more observations came in, the universe's early darkness looked less like an empty stage and more like a nursery brimming with impatient giants. Each black hole appeared to be consuming matter with a ferocity that bordered on reckless, swallowing gas, dust, and even the faint beginnings of stars before they had a chance to shine. Their galaxies, small and delicate, orbitally wobbling like fragile lanterns in turbulent winds, seemed almost overwhelmed by the very creatures they hosted, as though they were nothing more than feeding grounds for guests that had grown far too large. Researchers began to wonder. If something fundamental had been misunderstood, something buried deep in the physics of how matter collapses or how the earliest clouds behave under extreme pressure. Perhaps these black holes were born not from stars but directly from colossal gas clouds that bypassed the ordinary process of stellar life and death. Such a scenario would create far heavier seeds, allowing them to reach their observed sizes far sooner. But even these alternative theories, bold as they were, struggled to match the sheer scale of the growth Webb was revealing. The deeper the telescope looked, the more unsettling the story became. These black holes weren't merely large, they were aggressively luminous, shining with an intensity that betrayed the chaos around them. Gas spiraled inward faster than models allowed, heating to temperatures so high that their glow became one of the clearest signals from that ancient epoch. And every time scientists recalculated the timescales, the results remained the same. Something was vastly accelerating their growth. It raised a question that felt almost philosophical. How do you break the rules of time in a universe barely governed by them yet? These early black holes seemed to exist at the edge of what physics allowed, stretching theories thin like cloth pulled too tightly. Every explanation came with complications, and every attempt at rationalizing their mass led to broader mysteries. Perhaps the early universe wasn't peaceful but chaotic, so densely packed that collapse happened with violent efficiency. Or perhaps gravity itself acted differently under those primeval conditions, shaping structures at a pace we can no longer witness today. Some scientists even dared to wonder whether we were seeing evidence of new physics, something beyond our current understanding, exotic forms of matter, early turbulence, or unknown quantum processes that supercharged the growth of these cosmic beasts. It felt almost poetic, the idea that the universe in its youth might have played by different rules, experimenting with shapes and forces before settling into the gentler patterns of later epochs. These black holes, growing too fast and too large, might have been echoes of that ancient experimentation. And as the data continued to pour in, astronomers began to suspect that these rapidly growing black holes weren't rare exceptions, they might have been common. A startling thought: what if the early universe was filled with such monsters, shaping the evolution of galaxies from the start rather than waiting to emerge billions of years later? That would mean our understanding of cosmic history needed rewriting, not in small edits but in sweeping strokes that redefined how structure formed. These thoughts kept researchers awake at night, staring at spectral graphs and simulation outputs that refused to align. The black holes weren't merely breaking timelines, they were mocking them. For every model that attempted to tame their growth, the observations created new contradictions. The universe was offering a quiet but firm reminder that its earliest chapters might be stranger than the ones we read today. Even the way these black holes interacted with their galaxies seemed unusual. Instead of being gentle centers of gravity, they acted like disruptive anchors, shaping the flow of star formation and sculpting the structure around them. Their energy output blasted through their environments, blowing away gas that the galaxies desperately needed to grow. Yet somehow, even as they choked their hosts, they continued to expand at alarming speeds. The more Webb observed, the clearer it became that these early giants were not only massive but efficient. The universe, still warm from its birth, provided raw materials in abundance, and these black holes wasted nothing. Their accretion disks glowed like cosmic furnaces, turning the simplest hydrogen into breathtaking radiance. The same processes that today take eons seemed compressed into cosmic heartbeats. This created a kind of cosmic paradox. The black holes grew quickly because the universe was young, but their existence implied they had started growing even before the universe's conditions should have allowed for such rapid collapse. They were both products of their era and anomalies within it, as though they had stepped out of a timeline slightly misaligned with the rest of creation. Some theories proposed that perhaps the seeds of these black holes formed directly from dark matter, collapsing in ways ordinary matter couldn't. Others suggested that the earliest galaxies were far more turbulent than previously thought, their chaotic motions funneling mass into their centers with astonishing speed. Still, none of these ideas fully solved the puzzle, each leaving behind lingering uncertainties. As astronomers replayed the data, they noticed subtle hints that these black holes weren't simply passively growing, they were influencing their surroundings in ways that accelerated their own evolution. Their immense gravity reshaped the flow of gas, drawing material inward like cosmic whirlpools. Even the earliest light around them seemed to indicate a preference for rapid feeding, as though the universe itself were pushing matter toward them. Yet within this chaotic growth, there was an elegance, a harmony of forces aligning to create something extraordinary. It felt almost like watching a cosmic performance unfold, one choreographed by laws we had yet to fully understand. The black holes didn't just grow, they orchestrated their own expansion, turning the fragile early cosmos into a stage for their accelerated rise. And as Webb continued to push deeper, revealing even earlier structures, the existence of these overgrown giants became more than a curiosity. They became a challenge. Their presence demanded a re-evaluation of cosmic dawn. They forced scientists to rethink how galaxies form, how matter clumps together, and how quickly structures can organize themselves in a universe that had barely taken its first breath. The deeper one looked into this mystery, the more it felt like standing at the edge of a vast, dark ocean, one whose depths still held shadows untouched by theory. These black holes were hints, whispers, suggestions of secrets the universe had been holding for over 13 billion years. And Webb, with its unblinking eye, was finally beginning to listen. Their rapid growth suggested a universe more dynamic, more experimental, and far more unpredictable in its earliest phases than scientists had dared imagine. The rules we apply to later epochs might simply not belong here. Perhaps cosmic dawn had its own set of laws, its own tempo, its own fierce intensity that faded as the universe aged. These black holes, growing too quickly to fit the timeline, were relics of that era. And in the quiet reflection of late nights, researchers found themselves humbled. These impossibly large, impossibly young black holes were not mistakes or anomalies, they were truths, shining through time to remind us that the universe is not obligated to behave in ways convenient to our understanding. It moves at its own pace, writes its own script, and occasionally grants us glimpses of chapters we didn't know existed. In the end, what Webb uncovered was not just a population of unruly giants but a reintroduction to cosmic adolescence, a time when physics bent and stretched, when matter behaved with wild abandon, and when black holes, instead of waiting patiently for growth, surged ahead like creatures racing the expanding darkness. And as we continue to study them, the story grows deeper, stranger, and infinitely more wondrous. The direct collapse possibility, birth without a parent star. In the quiet imagining of cosmic dawn, when the first galaxies were little more than translucent clouds trembling under the weight of their own forming identities, some researchers began whispering a possibility that felt almost mythic. What if some black holes were never born from dying stars at all? What if they arrived fully formed, collapsing directly from colossal clouds of primordial gas before stars even had time to ignite? This idea, long considered exotic, began resurfacing with renewed force as Webb's observations showed black holes far too large to have been seeded by mere stellar remnants. The direct collapse model paints a picture not of slow, gentle stellar evolution but of rapid, violent descent, vast hydrogen clouds so massive and so uniformly dense that they skip the usual cycle of fusion, bypassing the entire sequence of star birth, life, and death. Instead, these clouds simply fold inward under their own immense gravity, collapsing into black holes that begin their existence already millions of times heavier than any stellar corpse. It is a dramatic, almost theatrical process, but one that suddenly seemed necessary to explain the monstrous giants glimpsed at the universe's youngest edges. What made this scenario so fascinating was how seamlessly it solved the growth problem. If a black hole begins life already enormous, then its rapid appearance in the early universe no longer violates cosmic timelines. It doesn't need to gorge for hundreds of millions of years to reach the masses Webb detected. It starts heavy. But even this explanation demands a universe primed for such extreme behavior. Gas clouds must remain pristine, without heavy elements, and they must avoid fragmenting into stars. Gravity must win the race against cooling forces, pushing everything inward in a single catastrophic motion. To imagine such a collapse is to picture an almost eerie calm giving way to a sudden inward rush. The gas cloud, initially silent and luminous only in faint infrared glow, grows denser at its core. Instead of breaking into tiny star embryos, it maintains its unity, its cohesion, as though guided by an invisible hand determined to create something far more extreme. In the final moments of collapse, temperatures spike, radiation struggles to escape, and the entire structure folds into a singularity, leaving behind nothing but a colossal black hole wrapped in the smooth drift of primordial hydrogen. Webb's discovery of unexpectedly massive early black holes breathed new life into this theory. Suddenly, what once seemed speculative became a viable explanation, maybe even the leading one. The spectral signatures coming from certain ancient galaxies suggested conditions nearly perfect for direct collapse: low metallicity, high density, and enormous reservoirs of material untouched by earlier generations of stars. These were the ingredients required for a direct collapse black hole to form, as though the early universe were cooking them deliberately in select corners. But even this scenario was not without its own mysteries. It required conditions so specific and finely balanced that one couldn't help but wonder how often they could have occurred. The universe at that time was chaotic, filled with turbulence and fluctuations that often encouraged fragmentation. For a cloud to remain intact long enough to collapse directly, everything had to align just right. And yet, if Webb's observations were accurate, such alignments may have been far more common than we previously believed. The thought that black holes could begin life without parents, without supernovae, without stellar corpses, was both unsettling and strangely elegant. It painted a universe much more creative, a cosmos willing to experiment with shortcuts to form its most extreme objects. Instead of waiting patiently for stars to rise and die, it allowed gravity to leap ahead, creating behemoths in silence long before the first starry constellations blossomed. These were not the black holes we were familiar with. These were ancient things, born directly from the universe's breath. Imagine, for a moment, the scale required. A cloud must be tens of thousands of times more massive than the Sun, yet stable enough to maintain its shape until gravity claims its victory. It must be heated not by starlight but by the very pressure of its own collapse. As it contracts, the growing density traps radiation, preventing cooling, which in turn stops it from breaking into stars. This is a perfection of timing, gravity pushing, heat resisting, fragmentation failing. In the last seconds, the center becomes so dense that no force can counteract the inward pull. A black hole emerges, silent as a whisper. Webb's infrared sensitivity allowed astronomers to detect the faint surroundings of these ancient objects, galaxies too small to host such giants if those giants were grown through ordinary accretion. The mismatch looked like a cosmic joke, galaxies in their infancy hosting black holes in their maturity. But with direct collapse, the mismatch became understandable. The galaxy was young because it came after the black hole. The black hole wasn't the result of the galaxy's evolution, it was the seed that shaped that evolution. And in that inversion, the story of cosmic dawn became more dramatic. Instead of galaxies giving rise to black holes, the earliest galaxies may have been sculpted around them. The black hole formed first, a massive gravitational anchor, and only later did the surrounding gas begin to swirl into stars and structures. This flips the narrative of cosmic history, suggesting that black holes may not be the byproducts of galaxies but their architects. Yet, not every observation fits neatly into this framework. Some black holes appear even larger than direct collapse seeds should have been able to produce. Others sit within galaxies whose metallicities seem too high for the pristine conditions required. Each exception forces scientists to consider additional possibilities. Perhaps there were multiple pathways, not just one. Perhaps the early universe was a laboratory of parallel experiments, each creating black holes through different extreme routes. Still, the allure of direct collapse remains strong because it feels like an ancient secret whispered from the universe's earliest pages. It is a story of gravity unchained, of matter falling inward before complexity could interfere. And it helps us understand why the early cosmos was dotted with bright quasars long before ordinary stars had matured. These quasars were likely powered by black holes so large that only direct collapse could explain them. The model also aligns with another quiet detail: the lack of intense radiation that massive populations of early stars should have produced if stellar collapse were the primary mechanism. If instead, huge gas clouds sank into themselves without igniting starlight first, the early universe would remain darker, quieter, and more aligned with observations. Direct collapse allowed light to emerge abruptly when the newborn black hole's accretion disk heated gas to brilliance. One can imagine the moment of ignition. After the black hole forms, the gas around it spirals inward, heating to millions of degrees. What had been a dim cloud becomes a blazing beacon, a sudden flare in cosmic darkness. To ancient galaxies around it, this flare must have appeared like a cosmic sunrise. For us, looking back 13 billion years later, its light is a faint whisper, but one powerful enough to reveal the impossible mass hidden at its center. And so the idea grows: maybe the earliest universe was seeded with dozens, hundreds, even thousands of these direct collapse giants. Maybe they shaped the clusters and filaments that now span billions of light-years. Maybe the large-scale map of the cosmos is written not by stars but by these black hole anchors, pulling matter into patterns we see today. If that is true, then black holes are not merely endpoints of stellar evolution but key players in cosmic formation itself. They were present before galaxies, before complexity, before the familiar rhythms of starbirth took over. They were the first architects, carving patterns that the rest of the universe followed. Even more intriguing is the idea that some of these ancient black holes may still exist today, their origins invisible but their masses immense. They might sit at the centers of modern galaxies, including our own, silent reminders of the universe's earliest experiments in gravitational collapse. The Milky Way's supermassive black hole may itself be a descendant of such a seed, its ancient roots buried under billions of years of growth and galactic history. As scientists run simulations, the results increasingly hint that direct collapse may not just be possible but inevitable under early universe conditions. The rapid formation of structure, the patterns of dark matter halos, and the turbulent flows of primordial gas all seem to converge toward environments where direct collapse becomes the simplest outcome. The universe, it seems, had plenty of opportunities to let gravity skip the intermediate steps. Yet even as this idea gains strength, it brings with it questions that tug at the boundaries of our understanding. What triggers a cloud to collapse directly rather than fragment into stars? How rare were these events? How many such black holes were born before galaxies? And perhaps most importantly, what does direct collapse tell us about the early laws of physics? Were they the same as today, or did the youthful universe play by subtly different rules? Webb's discoveries continue to nudge us toward answers, though never in straight lines. Each new data point is a hint, a clue, a ripple in the story. The ancient giant's web reveals behave as though they are children of direct collapse, massive from birth, quiet at first, then suddenly luminous. Their surroundings match the recipe for pristine clouds. Their existence makes sense only if they began life with tremendous advantage. In this sense, the direct collapse model is not merely a theory, it is a bridge. A way to connect the impossible to the plausible. A way to imagine a universe more efficient, more impatient, and more dramatic in its youth. And whether or not this is the full story, it offers a path forward, a direction for our understanding to travel, even as the darkness of cosmic dawn continues to guard its deepest truths. If you want the next section, just give me the starting line and paragraph count. In the dim half-light of cosmic dawn, the earliest galaxies were fragile, trembling structures, wisps of starlight and drifting gas held together by the faintest threads of gravity. And yet, hidden at their centers, something far older and hungrier pulsed with restless power. These black holes, too massive for their surroundings and too active for their age, behaved like lonely, greedy hearts beating inside bodies far too small to contain them. They consumed with a desperation that felt almost instinctual, as though they knew the universe around them was still soft, still pliable, still rich with easy nourishment. Their galaxies, by contrast, were little more than cosmic infants, cloudy, irregular, clumpy shapes still figuring out how to shine. They had barely begun forming stars, barely gathered enough mass to be considered full galaxies, and yet the black holes inside them acted like creatures already ancient. The imbalance was uncanny, enormous gravitational engines seated inside tiny, delicate hosts. It made these galaxies look like lanterns with flames far too large, flickering wildly as they struggled to maintain their structure around such overwhelming central force. Webb's observations painted these early galaxies as chaotic environments where matter swirled like mist around a whirlpool. Gas streams flowed inward at reckless speeds, guided not by orderly rotation but by the overpowering pull of their central black holes. Instead of forming peaceful, stable disks, the galaxies bent, stretched, and distorted as their cores devoured everything within reach. This wasn't gentle astrophysical evolution, it was survival, a frantic dance. Around an insatiable gravitational hunger. The loneliness of these black holes was almost poetic. They existed at a time when the universe was still mostly dark, when stars were rare, and galaxies were sparse islands separated by vast oceans of silence. There were no cosmic cities, no bustling clusters, no complex networks. Just isolated pockets of matter drifting through expanding darkness. In that solitude, these black holes grew as though trying to fill a void, their greed a response to the emptiness around them. But their greed came with consequences. As they fed, they unleashed torrents of energy that blasted outward, heating and stirring the gas around them. This radiation, powerful and relentless, sometimes prevented stars from forming, pushing away the very material their galaxies needed to grow. In a strange and quiet irony, the hearts of these galaxies were both their engines and their destroyers, nurturing growth while simultaneously choking it. They carved out cavities of hot, turbulent gas, reshaping their host galaxies like sculptors working with too much force. Despite these disruptive effects, the black holes didn't slow down. The early universe provided an abundance of cold hydrogen streams, cosmic rivers funneled along dark matter filaments. These rivers fed the black holes continuously, allowing them to grow much faster than similar objects do in the modern universe. It was as though they lived during a cosmic monsoon season, with rainstorms of matter pouring directly into their gravitational mouths. In such an environment, greed wasn't just instinct, it was opportunity. Astronomers realized that these early black holes were likely the dominant forces within their galaxies, shaping their evolution more profoundly than stars ever could. Instead of galaxies developing quietly and later forming black holes in their centers, these ancient systems were built around their ravenous cores from the beginning. The black hole was the anchor, the seed, the defining feature of the galaxy, its greedy heart dictating the rhythm of its growth. And yet, there was something deeply lonesome about their existence. Unlike the well-structured galaxies of later eras, these early systems lacked companions. There were no neighboring galaxies bustling with activity, no grand interactions or mergers to feed them in dramatic bursts. Instead, they grew in isolation, relying solely on the slow drip of cosmic gas and the faint inflow of matter from their surroundings. Their hunger grew in quiet places, lit only by their own fierce accretion glow. As Webb peered deeper into the early cosmos, it revealed the faint halos of these galaxies, wispy, irregular structures illuminated mostly by the energy their black holes released. It wasn't the gentle light of countless stars but the harsh brilliance of matter being torn apart. These galaxies didn't shine, they smoldered, glowing softly from the violence within their centers. Their light was lonely light, born from collapse rather than creation. The black holes seemed almost aware of their solitude, continuing to accumulate mass with an urgency that felt almost emotional. Without large populations of stars around them, without bustling star-forming regions, they seemed to be the only mature inhabitants in a universe made entirely of children. Their massive presence gave them an air of cosmic outsiders, objects that did not quite belong to their environments, yet dominated them completely. And the more massive they grew, the more their influence expanded outward. Their gravitational pull disturbed the formation of stars, their radiation heated the surrounding gas, and their jets carved narrow channels through primordial clouds. These actions shaped the architecture of their galaxies long before traditional galactic physics took control. They were like solitary monarchs ruling kingdoms still in the process of forming, their commands etched into the very fabric of their surroundings. Scientists began to realize that many early galaxies might never have been able to develop without their black holes. The gravitational centers created by these monsters helped pull matter together, stabilizing the structures around them. In this sense, the black hole was not just a destroyer but a midwife of galactic birth. Its presence ensured that the galaxy didn't disperse into the ever-expanding void, holding its scattered components together with an iron gravitational grip. Yet even as they played this stabilizing role, the black holes continued consuming at a pace that threatened to outgrow their hosts. Some galaxies looked as though they might be swallowed entirely if the feeding continued unchecked. The balance between creation and destruction was razor-thin, a fragile harmony in which the galaxy could thrive only if the black hole's hunger stayed just below catastrophic levels. It was a precarious relationship, like a flame kept alive by straw that might burn it all away if fed too quickly. Webb's spectral measurements revealed that some of these black holes were growing at rates close to or even exceeding the theoretical limits set by radiation pressure. This meant they were somehow accreting matter faster than physics should allow. Whether through dense gas flows, chaotic inflows, or unusual early universe conditions, these black holes were rewriting the rules of how quickly gravitational giants could grow. Their greed, it seemed, had found loopholes in the cosmic law. Their loneliness also amplified their impact. With few nearby objects to disrupt or compete with their feeding, the black holes enjoyed uninterrupted access to fresh material. In later eras, galaxies collided, merged, and tangled, creating complex feeding patterns. But in these early days, the environment was simple, just gas, gravity, and silence. In that simplicity, the black holes thrived like predators in untouched wilderness, their dominance absolute. Some models suggest that these lonely giants may have triggered waves of star formation by compressing gas as they fed, while at other times they may have quenched it entirely. Their influence was inconsistent, unpredictable, yet always profound. The early cosmos was a place of extremes, and nowhere was that clearer than in the dual nature of these greedy hearts, nurturing and devastating, sustaining and devouring. As these galaxies aged, some eventually gained enough mass to challenge their black hole's dominance. Star clusters formed, structures stabilized, and the balance of power shifted. But for millions of years, the black holes ruled alone, their presence the central sculptor of galactic identity. And even as stars began to fill the void, the memory of that early imbalance remained etched in the galaxy's cores, reflected in their motions and densities. What makes these early black holes so captivating is not just their size but the emotional atmosphere they evoke. They feel like entities growing ahead of their time, too large, too hungry, too isolated. Their existence paints the early universe as a place where shadows grew faster than the light, where gravity's loudest voices came long before the gentle whispers of starlight could fill the dark. The loneliness of these giants becomes even more striking when one imagines the distances between early galaxies, vast expanses of silence broken only by the faintest flicker of radiation. These black holes were monarchs without courts, rulers without subjects, eating not out of competition but out of cosmic instinct. Their isolation magnified their appetite. Yet this very loneliness made them perfect laboratories for understanding the raw mechanics of black hole growth. Without external disturbances, without mergers or complex interactions, their evolution was pure, a direct outcome of early universe physics. They showed us what black holes become when fed uninterrupted in pristine, untouched environments. They showed us how greed shapes creation. And in their quiet way, they revealed the truth that even in a near-empty universe, gravity finds a way to gather, consume, and grow. These were the universe's first engines, powering the earliest galaxies, lighting the earliest nights, and laying the groundwork for everything that would follow. They were lonely, yes, deeply so. But in their greed, they forged the foundations of cosmic structure. The story of these early black holes is a reminder that the universe began not in calm order but in restless hunger. The galaxies we know today may carry the faint echoes of those ancient, solitary hearts, giants that grew too fast, too early, too greedily. And as Webb continues to reveal their secrets, we come closer to understanding how the earliest darkness gave rise to the structures that now fill the cosmos with light. When black holes collide, a deep, distant roar. In the early cosmos, where galaxies drifted like fragile clouds in an endless ocean of darkness, a sound beyond human hearing was already beginning to echo across the void. It was not a sound in the traditional sense, but a ripple in space-time itself, a deep, distant roar created when two colossal black holes drew near and began the slow, inevitable dance of collision. Webb's observations could not directly hear these gravitational murmurs, yet it captured the aftermath. The shifting patterns of gas, the distorted starlight, the chaotic light signatures that hinted at unimaginable forces converging. Astronomers realized that these events were not just spectacular, they were transformative. When two supermassive black holes in tiny early galaxies approached one another, their gravitational pulls intertwined in a violent ballet, sending stars and gas into chaotic orbits. The galaxies themselves quivered under the immense tidal forces, stretched and bent like clay on an invisible potter's wheel. These collisions reshaped the structure of the galaxies, creating dense cores and feeding streams that accelerated star formation even as they heralded potential destruction. The energy released during such cosmic encounters dwarfs anything else in the universe. Matter spiraling toward the merging black holes is torn apart, heated to millions of degrees, and ejected in streams that can escape the galaxies themselves. Jets of high-energy particles blast outward, carving tunnels through interstellar clouds, while radiation floods nearby space with an intensity that makes entire star clusters shimmer. It is a destructive dance, yet one that seeds creation, a paradox of chaos and order stitched into the very fabric of the early universe. Webb allowed scientists to infer the presence of such collisions even billions of light-years away. By examining unusual spectral lines, abrupt velocity shifts, and asymmetric light distributions, researchers could reconstruct the story of these mergers. Each signature was like a ripple frozen in time, a silent testament to a gravitational roar that occurred when the universe was still only a few 100 million years old. The scale of the events defied ordinary comprehension. Two black holes, each millions of times the sun's mass, spiraling together across distances far greater than our solar system. Even in isolation, the effect of these collisions on their host galaxies was profound. Gas clouds were compressed, star formation was either triggered or quenched, and the galactic centers were violently rearranged. Unlike black holes growing alone, colliding giants left tangible scars, permanently reshaping the gravitational landscape of the cosmos. The aftermath was not instantaneous, it played out over millions of years, a slow-motion drama where the roar of gravity carved the destiny of young galaxies. The gravitational waves produced by such mergers are silent to human ears but detectable through ripples in spacetime itself. These waves carry the story of mass, velocity, and energy, stretching and compressing the universe as they travel. While Webb cannot measure these waves directly, the alignment of disturbed stellar orbits, distorted gas clouds, and glowing accretion disks provides indirect evidence. Each collision leaves a fingerprint, a subtle but persistent mark that testifies to the immense forces at play. Collisions were likely more common than previously imagined. In the crowded neighborhoods of early galaxies, interactions were inevitable. Tiny protogalaxies drifted into each other, their central black holes meeting as inevitable consequences of gravity. The universe was a playground of merging matter, where collisions shaped the pace of galactic evolution and dictated which black holes would dominate future cosmic landscapes. Each encounter was a chance for a black hole to grow exponentially, devouring its partners surrounding matter and expanding its own mass. The speed at which these mergers occurred is another astonishing factor. While gravitational waves propagate at light speed, the process of black holes spiraling together is incredibly slow relative to their internal scales. Yet in the context of the early universe, time itself was compressed, and these events happened on a scale that allowed rapid galactic evolution. Two black holes might orbit each other for tens of millions of years, their energy gradually radiating away until the final plunge, an elegant crescendo of spacetime itself. The collisions were not uniform. Each event varied depending on the masses involved, the orientation of spins, and the surrounding environment. Some mergers produced symmetrical ripples in the surrounding gas, while others sent matter careening in all directions. The resulting galaxies were equally diverse, from elongated, irregular shapes to surprisingly compact and dense cores. Webb's infrared vision could trace the resulting warmth of heated dust and gas, revealing the patterns that hinted at violent pasts. In some cases, the combined black hole resulting from a merger could achieve masses far beyond what a single galaxy could support alone. These new giants often dominated their host galaxies entirely, reshaping the dynamics of stars and gas within hundreds of light-years. Their gravitational pull became the central organizing principle, dictating the flow of matter, the orientation of orbits, and the pace of star formation. Mergers created rulers of unprecedented authority within the young cosmos. The light emitted from colliding systems often flickered unpredictably. As gas and dust were consumed at varying rates, the luminosity of the galactic core could spike dramatically, then fade, then surge again in unpredictable patterns. Webb's instruments could capture these subtle changes, helping astronomers reconstruct not just static images but dynamic histories, piecing together the sequence of gravitational events that led to present-day observations. Sometimes, black holes could even recoil after merging. The anisotropic emission of gravitational waves during the final stages of collision could impart enormous velocity to the newly formed black hole, sending it careening through space. These wandering giants could exit their host galaxies entirely or oscillate back and forth through the central regions, stirring up gas and stars as they went. The collisions were not just endpoints, they were triggers of new, complex cosmic activity. The scale of matter affected by these mergers is staggering. Gas clouds spanning hundreds of light-years can be redirected, compressed, or expelled entirely. Star formation may be ignited in some regions while quenched in others. Even nearby protogalaxies may feel the gravitational tug, altering their paths and initiating future collisions. A single event sends shockwaves not just in space, but in time, shaping the evolution of the surrounding universe. Jets emitted by colliding black holes carve channels through interstellar medium at nearly the speed of light. These high-energy streams heat surrounding gas, suppressing some star formation while compressing other regions to form dense, newborn clusters. The feedback from collisions is therefore both destructive and creative, a paradoxical balancing act that guides the growth of the early cosmos. It is a mechanism by which black holes govern the universe around them, long before complex galactic structures dominate. Simulations suggest that collisions in the early universe may have been key to explaining the surprisingly large supermassive black holes observed at high redshifts. Alone, accretion may have been insufficient to grow such massive objects so quickly. But mergers offered a shortcut, combining mass and momentum, creating gravitational engines capable of consuming enormous amounts of matter in relatively short periods. Webb's findings support this, showing numerous galaxies with massive central objects that likely grew through a combination of rapid feeding and violent unions. The violent interactions also generate turbulent disks of gas around the newly merged black holes. These disks radiate in the infrared, emitting heat and soft light that Webb can detect across billions of light-years. By mapping these emissions, scientists can infer the dynamics of the mergers, reconstructing how matter flowed, twisted, and spiraled before finally falling into the hungry cores. Each disk is a fossil record of a gravitational symphony billions of years in the making. The echoes of these collisions extend far beyond the immediate galaxies. Gravitational waves propagate throughout the universe, leaving subtle imprints on the cosmic microwave background and the large-scale distribution of matter. While these effects are faint, they suggest that mergers influence not just local structures but the overall architecture of the cosmos. The universe remembers every collision, encoded in both light and gravity. Interestingly, not all mergers are catastrophic. In some cases, black holes approach each other gently, their spirals slow and measured. Gas around them can form stable rings or disks, providing sustained feeding for billions of years. These long-term mergers create conditions conducive to orderly growth, resulting in galaxies with massive central black holes that still maintain some structural coherence. Webb's infrared observations hint at both extremes, violent chaos and controlled accretion. The frequency of collisions decreases as galaxies age and the universe expands. Early on, when protogalaxies were densely packed, interactions were inevitable. But as space stretched, the likelihood of direct encounters dropped. This means that the early universe was a particularly volatile period, a time when black holes were most likely to collide, merge, and assert their dominance over forming galaxies. These ancient roars, therefore, belong to a fleeting era of cosmic intensity. Even in the aftermath, the effects linger for millions of years. Stars orbit irregularly, gas clouds continue to settle into new configurations, and jets carve persistent structures in the interstellar medium. The gravitational impact of a merger is effectively permanent, altering trajectories and redistributing matter long after the initial collision. The universe is, in a sense, scarred by every such event, a subtle map of ancient roars. Webb allows us to see these scars in exquisite detail. Infrared mapping of distant galaxies reveals asymmetries, elongations, and hot spots that hint at past black hole interactions. The faint distortions are the whispers of collisions, telling us not just that these events occurred, but how profoundly they shaped the earliest structures. The telescope's ability to detect these details transforms abstract theory into tangible observation. The mergers also help explain the formation of the largest supermassive black holes observed at high redshift. Alone, accretion is often too slow to reach billions of solar masses in under a billion years. Collisions offer a mechanism to accelerate growth dramatically, combining mass and energy in a fraction of the expected time. The early universe, therefore, relied on these gravitational symphonies to build its heaviest inhabitants. Each collision is unique, creating outcomes as varied as fingerprints. Some black holes merge and settle quietly, growing steadily without extreme feedback. Others ignite cataclysmic flares, ejecting matter at relativistic speeds and quenching star formation. Webb's data hints at both types, revealing a diverse population of post-merger galaxies that collectively tell the story of a universe defined by violent, transformative interactions. By studying these distant roars, astronomers are beginning to understand the rhythm of early cosmic evolution. Collisions dictated the pace of growth, the distribution of matter, and even the formation of subsequent galaxies. Black holes were not passive participants, they were active directors, orchestrating the flow of energy and matter in ways that left enduring fingerprints on the universe. Each event is a chapter, each ripple a verse in the story of cosmic creation. And so, these deep, distant roars are not merely distant echoes, they are the voice of the universe itself, speaking across billions of years. They tell of lonely giants meeting in the void, of galaxies trembling under tidal forces, of matter dancing to the tune of gravity. They reveal that from the earliest moments, black holes were not just observers of cosmic evolution, they were its conductors, its sculptors, its roaring hearts. The story of colliding black holes teaches us that even in isolation, in the earliest and most fragile galaxies, forces of unimaginable scale governed the growth of structure. Their mergers shaped the universe with both subtlety and ferocity, leaving marks detectable billions of years later. Webb allows humanity to witness this, to trace the echoes of these ancient roars, and to understand that the first acts of cosmic drama were played out not in silence, but in gravitational symphonies that still resonate today. If you want the next section, provide the starting line and paragraph count.